When New Horizons flew past Pluto in 2015, the world saw a frozen wasteland. But the data told a different story. Pluto's atmosphere was too cold. Its haze was too tall. The numbers refused to add up. For years, NASA stayed quiet, but now in 2025, the James Webb Space Telescope has uncovered what was hidden: a mysterious glow, anomalous pulses, and a buried sphere beneath the ice. This isn't just about Pluto anymore. It's about what it might be: a machine, a signal, or something else entirely. Because what Webb found doesn't belong to nature as we know it. A frozen world and a hidden anomaly. In July 2015, the New Horizons probe zipped past Pluto, capturing glaciers of nitrogen, towering mountains of water ice up to 3 kilometers high, and vast plains stretching hundreds of kilometers. The heart-shaped basin known as Sputnik Planitia stood out, sculpted by frozen flows. This lonely outpost at approximately 39 astronomical units from the Sun was revealed as active, not dead. Its surface was a tapestry of ice and shadow. Yet the atmosphere told a different story. Temperature readings of the upper layers found values of around 203 degrees, approximately 70 Kelvin, roughly 30 degrees, colder than models predicted for a nitrogen-methane atmosphere. This mismatch flagged a hidden process, something pulling heat out of the sky faster than expected. The anomaly was real. Hovering above the surface was a bluish haze, reaching approximately 300 kilometers in altitude and layered into roughly 20 or more strata. The multi-layered haze caught the sunlight, scattering light like silk above the icy plains, even in twilight. Its height and extent were far beyond what a tiny dwarf planet might normally sustain. Scientists were puzzled. Gas-only models of Pluto's atmosphere couldn't account for the steady cooling and the atmospheric escape of methane and nitrogen. The whisper spread. What if something unseen high above Pluto's icy plains was regulating the climate? A mechanism beyond our textbook models, a hidden engine in the sky. That hidden engine led to a bold hypothesis. In 2017, researchers proposed that Pluto's haze wasn't passive dust. It might actively control the climate. In 2017, planetary scientist Xi Jiang proposed that the haze particles in Pluto's upper atmosphere could dominate its thermal balance. Previous missions had ignored the role of solid particles, focusing on gases like N2 and CH4. Yang suggested instead that tiny solid tholin particles could absorb UV sunlight and re-emit energy in mid-infrared, acting like a giant radiator in space. According to the hypothesis, if the haze truly cooled the atmosphere, Pluto should emit a faint but distinct mid-infrared glow at wavelengths around 15 to 25 micrometers. But detecting that glow required the right instrument with enough resolution to separate Pluto's signal from its large moon, Charon. Previous telescopes lacked that precision. On Earth, climate models assume gases like carbon dioxide and H2O dominate energy exchange, with solid aerosol particles playing a secondary role. But Jiang's idea flipped that script. On Pluto, solid particles might be the script. It challenged planetary physics. If true, the haze wasn't just a backdrop, it was the thermodynamic engine. The challenge loomed. Could any instrument isolate the haze emissions in mid-infrared, separate from Charon, and capture light curves at 18, 21, and 25 micrometers? Until that day, the question remained, was Pluto's atmosphere passive, or was it being regulated by its sky? Then came the arrival of a game-changer, the James Webb Space Telescope with its MIRI instrument. Scientists held their breath. Would the haze glow show up? When JWST became fully operational in 2022-2023, teams targeted Pluto and Charon with the MIRI instrument capable of capturing spectra from 4.9 to 27 micrometers and photometric light curves at 15, 18, 21, and 25 micrometers. These wavelengths were precisely those predicted by Jiang's 2017 theory. Scientists held their breath. Could they separate Pluto's faint mid-infrared glow from the dominant signal of Charon? For years, the two were blended in telescope beams, but MIRI's resolution finally allowed distinct separation of the two bodies' thermal emissions. Observing runs began in May 2023. The tension mounted. What if the glow didn't appear? What if Pluto remained cold and quiet, as models had struggled to explain? The investigation hinged on whether the haze was visible in the infrared, if it truly was radiating away heat. For months, the data streamed in from deep space. Then results emerged. The mid-infrared curve showed anomalous emission, consistent with haze-driven cooling. Pluto's atmosphere appeared in a new light, literally. The icy world at the fringe of the solar system was no longer just frozen. It was broadcasting its secret. With the observations in hand, the team could say one thing: the haze glow was real. In May 2023, the James Webb Space Telescope captured what astronomers had long suspected. Pluto's upper atmosphere wasn't just scattering light, it was glowing. The MIRI instrument detected mid-infrared emission far stronger than could be explained by surface ice alone. The haze, it turned out, was not a byproduct. It was the source of the missing energy. Light curves collected at 15, 18, 21, and 25 microns showed periodic fluctuations in brightness, syncing with Pluto's 6.4-day rotation. This wasn't just heat. It was patterned emission rotating with the planet. It revealed an interplay between the surface and haze layers, like gears moving together in a machine. When the researchers subtracted the thermal contribution from Charon, Pluto's moon, the haze, stood out even more. Spectral signatures matched the predictions made by Zhang's model 6 years earlier. Pluto's haze wasn't passive. It was actively regulating atmospheric heat, cooling the entire system from above by radiating energy back into space. The implications were profound. For decades, scientists had assumed gaseous molecules like CO2 and CH4 dominated planetary climates. But here, solid particles, tholins, were running the show. This wasn't just a new finding for Pluto. It was a new planetary paradigm. Webb's spectroscopic analysis revealed Pluto's haze was made of tholins, complex hydrocarbons formed when methane and nitrogen react under ultraviolet light. These particles are tiny, solid, and chemically rich. They absorb high-energy photons and re-emit infrared radiation, turning sunlight into cold. This photochemical process doesn't just affect the atmosphere. As tholins settle, they alter the surface. Pluto's reddish tones seen in Sputnik Planitia and surrounding regions are layered with these haze particles. The climate and geology are linked by a continual snowfall of organic compounds. The chemical makeup of the haze is striking. Some tholins contain nitrogen-oxygen bonds, similar to precursors of amino acids on Earth. Under the right conditions, these particles could undergo further reactions. On our planet, similar chemistry in the upper atmosphere helped spark prebiotic evolution nearly 4 billion years ago. In Pluto's case, the haze behaves like a planetary thermostat, a photochemical exoskeleton regulating temperature and light. It's not alive, but it acts like a system. Charon, Pluto's largest moon, orbits just 19,040 kilometers away, close enough to be affected by Pluto's atmosphere. Webb's data revealed that methane escaping from Pluto was drifting toward Charon and transforming its surface. When this methane hits Charon's cold poles, it undergoes chemical changes under solar ultraviolet radiation, forming red tholins similar to those on Pluto. These reddish stains observed on Charon's north pole since 2015 are now understood to be directly caused by atmospheric leakage from Pluto. This planet-moon interaction is unique. No other body in the solar system shows such a clear case of atmospheric exchange and chemical transformation. It links the surface of one world to the atmospheric breath of another. In a sense, Pluto is painting Charon slowly, layer by layer in chemical shadow. Scientists now see Pluto and Charon not as separate entities, but as a coupled system: atmosphere, haze, chemistry, and geology forming a dance across two worlds. After confirming Pluto's haze as an active cooling system, astronomers turned their attention elsewhere. Could similar haze-driven thermodynamics exist beyond Pluto? Webb's infrared eye scanned Titan, Triton, and other outer worlds, and what it found was extraordinary. Titan, Saturn's largest moon, has long been cloaked in orange haze. But Webb detected mid-infrared emissions there too, nearly identical to Pluto's glow, only stronger. The signal on Titan was concentrated in the 15-25 micrometer range, matching the exact signature of radiating tholins. These emissions also fluctuated with Titan's rotation, suggesting its atmosphere might participate in a similar cooling cycle. Even Neptune's moon Triton, previously assumed to be geologically quiet, showed signs of subtle infrared activity. Though fainter, the signal hinted at nitrogen-based haze particles releasing energy through the same thermal mechanism. Webb's findings suggested an entire family of icy bodies, Pluto, Titan, Triton, may share this kind of climate regulation. What we thought were passive frozen worlds are actually dynamic, chemically reactive systems.